So the next section we're going to talk about is adding resiliency to our layer 3 topology by implementing first hop redundancy protocols. And there are 3 different first hop redundancy protocols that exist in the Cisco world. Number 1 is HSRP, the Hot Standby Routing Protocol, or Router Protocol, whichever one you want to say, is a Cisco proprietary first hop redundancy protocol that provides us the ability to actually create a virtual gateway with a virtual MAC address and virtual IP address for the clients in our network. So that gives them the ability to fail over from one physical device to another physical device in the event that there's a failure. And that's really kind of the whole point of these first hop redundancy protocols, is to give us that capability. Now, VRRP, very, very similar to HSRP. Some slight differences with regard to preemption and the multicast group address and a couple of other things, but 99% the same. VRRP is the Virtual Router Redundancy Protocol. That's essentially the open standard version of HSRP. And then there's another one, which is a Cisco proprietary option, which isn't covered in this class. Probably in the Advanced Routing and Services class we might see it, is GLBP, the Gateway Load Balancing Protocol. It is the only one of the 3 first hop redundancy protocols that gives us the ability to actually use all the gateways at once. I might mention or talk about it a little bit later on. It would include things like an active virtual gateway and an active virtual forwarder. The AVG is the router that's actually technically responsible for handing out or distributing the load across the nodes that are part of the group. And then the active virtual forwarders are the routers that are actually the ones that are forwarding information. Okay, so that's what we're going to talk about in this section here. We'll talk about specifically 2 of these, HSRP and VRRP. So why do we have to have gateway redundancy? When we assign addresses to our PCs, when we assign addresses through DHCP, we assign them a default gateway. And that default gateway is used to reach the rest of the world outside of the subnet. And it's typically either statically configured or we have a single gateway that's assigned through DHCP. We could get away without using a gateway if we used a feature called proxy ARP, where essentially any router could respond to an ARP request that goes out to a host on the internet. But the problem with proxy ARP is ARP information gets cached. So even if I'm using proxy ARP to kind of dynamically assign the gateway to the clients, that information is cached for a certain amount of time. And if that device fails, it still won't fail over because we've cached that information and we don't have any instruction on the need to do an additional or implement kind of an additional query to get the new MAC address information. All right. So what we'd like to do is we'd like to have a way that the clients could have a gateway assigned, but that gateway is somehow virtual. And upstream devices like upstream routers can then take those virtual addresses and take control of them and manage the traffic flow for those virtual addresses, whether it is an IP address or a MAC address. In the case of both of these protocols, HSRP and VRRP, actually all 3 of them, we do that. We assign a virtual IP address and we assign a virtual MAC address, and then we have a router in the topology that's responsible for acting as the chief or the control point for those particular addresses. If that device fails, then those addresses move over to the other device. And that's kind of the whole point of a first hop redundancy protocol. All right. How many gateways typically does a client have configured? The answer is 1, right? It's unless the client is actually running routing itself, which used to happen back in the day. Vrrp used to be a host-based routing protocol as well as a router-based routing protocol. And ISIS had, which was intermediate system to intermediate system, had ISES, which was intermediate system to end system options as well. So we could actually do routing on the end system. But with a default gateway, it makes our lives much, much simpler. So we typically would only have one gateway assigned in this case. All right. So what is a first hop redundancy protocol? Is set in essence, and in each version of these first hop redundancy protocols kind of operate differently. HSRP and VRRP are very, very close to each other. There's only some minor differences between them. But the ultimate goal of any of these first hop redundancy protocols is to create some virtual IP address and some virtual MAC address that can be used on the client as the gateway resource. And then we would have 2 or 3 or 4 or 5 different routers in a standby group that would act as the actual physical devices that are providing the forwarding, and that virtual IP address and that virtual MAC address would be controlled by one of those physical devices within that group. The group would monitor itself, and it would have self-healing capabilities. So if one of the devices failed within that group, another device would simply take over the virtual IP, take over the virtual MAC address, and the process would continue on. The client would have really no indication that a physical device failed because it's still using that virtual IP and that virtual MAC address. So that is the general concept of creating this first hop redundancy group, which can be done, by the way, at layer 3 and layer 2 because of that virtual IP address and virtual MAC address. Like I said, there's 3 different versions of this first hop redundancy protocol. There's the hot standby router protocol, which, even though it is Cisco proprietary, there is an RFC that defines it, RFC 2281. VRRP, the virtual router redundancy protocol, provides some differences, but the major difference with VRRP is that it is open standard. It's not a Cisco proprietary protocol, and it is RFC 5798. Now, in both of these particular first hop redundancy protocol options, we only have one active forwarder. We can have multiple routers in the group, and whether they're called active and standby and candidate, or whether they're just called active and standby, doesn't really matter, but we can only have one active forwarder in the group. In this case, that would be the router that wins the election, if you will, and we'll learn how that happens as we start to get into the protocol itself. GLBP, the Gateway Load Balancing Protocol, Cisco designed as well, but in this case, every router is an active forwarder. And we have a chief of the group called an Active Virtual Gateway, or an AVG, that responds to all of the client ARP requests with virtual MAC addresses of members of the group. The virtual IP is shared among the group, but the virtual MAC addresses are unique on each of the forwarders, and the Active Virtual Gateway responds to the ARP requests based on a loading algorithm that it uses to decide which routers get which traffic. So it can be equal cost, or it can be, you can actually specify different loads that you want to apply to different routers, because you may not have the same type of routers that are connected to the segment. So one router might be more active than other routers because it just simply has more processing power or more CPUs or whatever. And that's the general idea. All right. Now, the only thing that's left to learn about is how do we configure these protocols? What are the nuances, right? How do they identify that there's a failure event? How long does that take? Can we tune that? Is there authentication that we can run to ensure that the process, the integrity of the process is maintained? Is there other different versions of these protocols? And what about doing upstream tracking, right? We monitor the group on the downstream link within the broadcast domain that we're servicing, but we don't monitor by default the upstream path. So if the upstream path fails, but the downstream path does not fail, then there is no failover event with regard directly to HSRP or VRRP, and that means that we might have suboptimal routing, or we might have a black hole because we didn't account for monitoring that upstream traffic. So we can use things like objects, IPSLA with tracking objects, and interface tracking to identify if there is a failure upstream that would cause us to force a switchover within the group itself. All right. So when a route fails, maybe we lose a link on the downstream side. That's the kind of the simplest way to identify a failure. The standby router stops getting the hello messages from the forwarding router. And so the standby router is passive. It's sitting there waiting to see these keep alives from the active router. So after a certain amount of time, there's a dead timer involved. In the case of HSRP, it's 10 seconds. But after a certain amount of time, I'm going to say, oh, that router doesn't exist anymore. I guess it's my responsibility now to take over the role as the active router for this group. And again, the client is completely unaware, right? Because it's still the same virtual MAC address. It's still the same virtual IP address. So what is HSRP? HSRP is a first hop redundancy protocol that was designed by Cisco to create a redundancy framework between a network routers or switches to achieve a default gateway failover capabilities. Yeah, I guess that sounds about right. Kind of a long-winded description, but it's true, right? HSRP is a peering feature in the hot standby router protocol group member health monitoring system. No. HSRP is a hot standby router protocol that needs low CPU memory consumption and no processing overhead. Low CPU I would probably agree with. No processing overhead I would not agree with, right? Because we still have to manage the group. We still have to send keep alives back and forth, and we still have to be able to identify whether a failover event occurs. Plus, there's an election process that takes place as well. So we have to exchange information periodically for that to happen. HSRP is an FHRP open standard. Nope, it's Cisco proprietary. Okay? All right, welcome back, everybody, to our discovery. In this discovery number 12, implementing HSRP, the Hot Standby Router Protocol. It's a Cisco proprietary protocol, as we discussed in our lecture series. It was developed to allow multiple switches, multi-layer switches or routers, to appear as though they are a single gateway. So throughout this discovery, we're going to work with HSRP. We have a couple of hosts on the network. A host would normally only have a single IP address that gets configured as its default gateway. But of course, HSRP allows two physical routers, or even more than two physical routers, to work together in an HSRP group to provide virtual IP addresses and an associated virtual MAC address as well for that particular group. All right. Now, the end host would use that virtual IP address as their default gateway. They would learn the virtual MAC address through the standard address resolution protocol process. One of the routers in the group is going to act as an active router, and it's going to be responsible for the virtual MAC address and the virtual IP address, and the other routers are going to be in a standby state. The other router, I should say, because we only have one standby router in HSRP, and it's going to monitor the active router. We'll take a look at that. We're going to do a Wireshark capture on this link here. In fact, let me go ahead and start that capture so that as we start to do our configurations, we will be able to see the process, if you will, of communication between the peers. And we're going to take a look at some of the nuances and some of the specifics of HSRP. All right. For example, what is the virtual MAC address? How do the routers communicate? What is the keep alive process? And so on. So in this lab, we're going to learn how to configure HSRP parameters. We're going to set up an HSRP group. We're also going to work with different HSRP priorities and identify different priorities within HSRP to influence the election process. We're going to take a look at HSRP preemption as well. And we'll also take a look at different HSRP timers, different HSRP states, and so on, so that we can see how the process works. All right, let me kill this. It didn't seem to load there for some reason. So we'll try it on a different link here. Now, keep in mind, this is not a typical topological design that you would see in most enterprise networks. Because HSRP is a process that can either run on layer 3 switches or routers, we normally would see this simply run on our multi-layer switches as part of the SVI / multi-layer switching configuration. All right, but HSRP in this particular case is going to be configured on router 1 and router 2 because of this special build of iOS for Linux, or what we call IOL. The lab does not use the switches in those software versions, simply don't support the HSRP feature. So we're just going to have to configure this on our routers. But you know, overall the concept is still the same. Nothing really changes from that perspective. All right. So the first task that we're going to go through here is how do we configure and tune HSRP to function, right? So first of all, we need to understand the protocol itself. We did a little bit of that discussion in our lecture series, but I'm going to do a little bit of review in this one as well with regard to what we see between router 1 and router 2 in this particular case. Right? HSRP, the hot standby router protocol, it is a first hop redundancy protocol, not a load balancing protocol, but a redundancy protocol. And it allows for the transparent failover of the first hop that the client devices are going to be using as their default gateway. Most most hosts are going to have a single IP address of a router configured as their gateway. So if we were not running some sort of first hop redundancy protocol, if that device were to fail or reachability to that particular location were to fail, or that address were to fail, then we would simply not be able to communicate beyond our subnet. So in this case, we're going to use HSRP, where we're going to create a virtual IP address that's going to be configured as the default gateway for the host instead of the IP address of the actual physical router. All right. HSRP defines a group of routers. Within that group, we can have 3 different roles, right? We can have an active router, we can have a standby router, and then we can have some candidate routers as well. A virtual IP address and a virtual MAC address are what we're going to use to manage the HSRP domain, at least to represent the HSRP domain, I should say, with regard to what is the virtual IP and MAC address that the clients are going to use to communicate. Now, both of these values we can define. One has to be defined and shared between the group members. That's the virtual IP address. The other is automatically derived, but it can be changed, and that's the virtual MAC address. To verify the HSRP state, we're going to use pretty much a single basic command, show standby, and that's what's going to allow us to verify the state of HSRP. HSRP is a Cisco proprietary protocol. VRRP, which we're going to talk about next, and we're going to go into a discovery next, is equivalent to essentially the open standard version of HSRP. There are some slight differences between those protocols, specifically with regard to preemption, interface tracking, whether or not we can use an interface physical IP address or not as the virtual IP, and so on. All right, but we'll get into that discussion a little bit later on. Now, HSRP defines a standby group of routers. One router is going to be designated in this particular case as the active router. And then we, of course, provide that gateway redundancy by sharing the virtual IP address and the MAC address between the redundant gateways. The protocol itself consists of a virtual MAC, a virtual IP address, and 2 or more routers that belong to the same HSRP group within the same broadcast domain. All right, so some of the terms that you might see as you're exploring your understanding of HSRP is, what is an active router? Well, the HSRP active router is the one that's currently housing the virtual IP address and virtual MAC address, and it is the one that is actually forwarding packets for the broadcast domain. The standby router is the primary backup router to the active router. And then what we also define as the overall group is what we call the standby group. Basically, it's our group of routers that are participating in this emulation of a virtual router in the HSRP environment. Now, the HSRP active router has some basic characteristics. It's the one that's going to respond to all of the gateway ARP requests for that virtual MAC address that the clients are going to use for their layer 2 forwarding within the broadcast domain. It also assumes all of the active forwarding of the packets of the virtual router IP address as well. Interestingly enough, the active router is the one that sends the hello messages, and then the standby router passively looks for those hello messages to identify whether or not the active router is still active. All right. It's also the one that has the virtual router IP address. Now, the standby router also sends hello messages, but it's also listening for those periodic hello messages. And if it doesn't see those hellos for a specific hold down period, it's going to assume the active forwarding role for the packets that it does not hear from the active router. So essentially, hosts on the IP subnet that are going to be protected by this HSRP configuration, their default gateway is going to be that HSRP group virtual IP address. All of the packets that are received on that virtual IP address would then be forwarded to the active router. That's, of course, going to be the responsibility of the layer 2 switching domain based on standard MAC address forwarding and flooding rules. All right, the function of HSRP, specifically the standby router, is to basically just monitor the operational status of the group. Now, it only does that by default on the broadcast domain that it's responsible for, right? So, for example, we don't by default monitor upstream links. We can certainly configure that with things like IPSLA and object tracking. We monitor the broadcast domain, the downstream links, and that's where those keep alives are going to be sent, those hello packets, and that's where we're monitoring the progress of the group. All right. Now, there are many different tuning options that we have with HSRP, and I'll probably try to talk about a little of those in this section here. The ENCOR class doesn't really get into a whole lot of detail on that, but I'm going to go through a couple of the different options that we have with HSRP and maybe even demonstrate some upstream tracking options as well. All right. HSRP overall is a Cisco proprietary protocol. VRRP is a standard protocol. The differences between them pretty slight, and we'll see this between HSRP and VRRP as we do our discovery number 13, which is our VRRP discovery. All right. It has to do with primarily the group setup, group numbering scheme that we can use, how many groups we can have, multicast address that's used for the processing of HSRP datagrams, and so on. All right. Now, incidentally, configuring HSRP is relatively simple. An HSRP group is basically just a set of devices that emulate a virtual router, and we actually set up that virtual IP by going into the interface. In this case, it's going to be on the downstream interface, and we're going to go in and say standby, specify the group number, put in the syntax IP, and then specify the virtual IP address. Now, by default, the group number is set to 0 if you don't specify a group number. In HSRP version 1, that group number can be any integer between 0 and 255. It gets larger if we go to HSRP version 2. All routers in the HSRP group exchange hellos with each other. The roles of the routers in the HSRP group are based on those exchange of hello packets. All right. Now, for HSRP 1, version 1, I should say, we actually send the traffic to 224.0.0.2, and we'll take a look at this in our Wireshark Capture as part of the process. But 224.0.0.2 is not really a application-specific group multicast address. It's basically just the all routers multicast address. Also, it's going to be sent over UDP port 1985. So if there's something in between these devices that might be filtering out UDP traffic or UDP port 1985, the keep alives will not pass, the hello packets will not pass, and the routers will think that there's a failover event. All right. Now, in this particular lab, we are going to assign both routers to a common group, group 1, and then we're going to configure HSRP for, the various parameters. Now, If I wanted to configure HSRP, say for example on a multi-layer switch, generally speaking, it would be beneficial to create the HSRP group number to match the specific VLAN. So, it doesn't have to match the VLAN, but it would be very useful if for documentation purposes and for troubleshooting purposes to see that. Now, the group numbers themselves are actually locally significant. So HSRP group 1, for example, on VLAN 22 is independent from HSRP group 1 on VLAN 33. The group numbers do have to match between the physical devices, but it doesn't really matter if you have overlapping group numbers across broadcast domains, because remember, this is a protocol that runs generally within the broadcast domain and not outside of the broadcast domain. Now, one of the two routers that are participating in the group are going to have to be elected as the active router, and then the other router is going to be elected as the standby router. If I do have more routers in the group, they would be kind of stuck in a listen state, and then they would be what we would basically consider as HSRP candidates. All right, so we do not, unlike VRRP where we have multiple standby routers, in HSRP we only have one standby router. Okay, not that other routers couldn't be part of the group. Now the roles are elected based on the exchange of these HSRP hello messages. When the active router fails, the other HSRP routers stop seeing those hello messages from the active router. The standby router then assumes the role of the active router, and then if there are other routers participating in the group, they would contend for the role of the new standby router. Now, if both the active and the standby routers fail, all the other routers in the group would then contend for the active and the standby routing roles. All right. As the new router becomes active, both that virtual IP address that gets created within the group and the virtual MAC address gets taken over. Essentially, outside of the amount of time it takes for that failover event to occur, the end stations really see no disruption in service. They're going to continue sending their packets to the virtual router, and then that new router is going to start forwarding those packets. All right. Now, we also use the Icmp protocol. The Icmp protocol allows the router to redirect an end station to send packets to a particular destination. So if the first router knows that the other router has a better path to a particular destination, when we had this with default gateways, if the router that the end station had been redirected for a particular destination, if that router were to fail, then the end station packets to the destination would not be delivered, I should say. All right. For HSRP, this is exactly what happens. So it's important in this particular case for HSRP as a best practice configuration, disable Icmp redirects once you've configured HSRP. A lot of cases that's already disabled by default. So we're going to go in and do a basic basic configuration here. You can see we're doing a capture here on the network. I actually decided to go ahead and capture on this link right here, but it is part of the same broadcast domain, so I should still be seeing everything that I need to see. So let me go into router 1, and let me just do a quote show IP interface brief, make sure my interfaces are up, and I'm going to try and ping 2.2. That's kind of a general recommendation, right? Just kind of make sure that you have basic reachability before you start to do anything else, because if you don't have reachability, what's the point of trying to configure that reachability in the standby in the process, right? So make sure everything works first, and then you can go through and start to do your HSRP configuration and so on. So our first activity here in step 1, we're going to configure this Ethernet 1.1 interface. That's the LAN-facing interface. With it has an IP address of 1.3, by the way, and that's going to be relevant in a minute, with an HSRP group number of 1, and we're going to set up a standby IP address of 1.1. So we're going to go config T, interface Ethernet 1.1, IP address 192.168, although it already has the address. We'll just go ahead and put that in here. 255.0. And we're going to say simply standby. Notice here that I have group numbers 0 through 255. We're going to talk about a lot of these other options as well, but we're going to be using group number 0 through 255. In this case, I'm going to use group number 1. Now you'll notice as soon as I do that, I should start to see some sort of HSRP messages being generated. Let's see, I'm seeing spanning tree, loop prevention mechanisms. In fact, let's go ahead and filter that. Oops, let's clear that filter. I meant to clear that out. Apply filter not selected. Let's get rid of our CDP. Apply filter and not selected. And let's get rid of our loop prevention mechanisms. Apply filter and not selected. All right. So we're not seeing messages as of yet. We do see active. Not sure why I'm not seeing the hellos, but let's go ahead and continue with our configuration. So ultimately, this is actually really the only configuration that needs to be applied in order for the router to be running HSRP. Obviously, though, one of the things that we would want to do is we'd also want to go through the process of making sure that we're tuning HSRP to operate as a best practice, in a best practice environment, right? Don't use the 3 and 10-second timers. Make sure you use HSRP group 2. Make sure that you configure authentication and so on. But we're going to kind of add to the layers of the configuration here. Let's go ahead and also do the same thing on router 2. Let me do a quick show IP interface brief. Now, that may be the issue. That would be the issue. Let me make sure I do show IP interface brief. Oops. Make sure I applied the configuration correctly. Ethernet 1.1 up. Let me just verify one thing here. Ethernet 1.2. Okay, so that would be why we're not seeing that information. We have an incorrect link here. So let me stop that capture and delete that link. That's why we were not seeing any of those messages. So let's go ahead and change that. There we go. And I'm probably going to, I shouldn't have to reapply the configuration. Do show run interface Ethernet 1.1. Yep, we're good there. So let's go ahead and start the capture again. And I should see those keep alives now every 3 seconds. Now, because the router didn't see any other, it went to a listen state for a short period of time, but because it didn't see any other routers claiming any kind of role in the HSRP group, it went ahead and elected itself as the active router for the group. But it is important to kind of see some of these messages. So here we go. Here's that is an EIGRP message. Let's filter that out. Apply filter. Let's do apply filter not selected. And let's get rid of our spanning tree. Apply filter not selected. Oops, I forgot to do and not selected. Well, here we go. Let's look at this first. I'll apply the filters here in a second. So this is the HSRP datagram, right? Again, the source port and the destination port 1985. So that's what we discussed in kind of our lecture component. As far as the IPv4 version information, destination IP address is 224.0.0.2. Notice that the time to live is also 1 here, which means this is a non-routable datagram. It's but it doesn't need to be routed, right? It's supposed to be within the broadcast domain. But let's take a look at the HSRP information. This is a hello. The current state that we're advertising is active. The default hello interval is 3 seconds. The hold time, the dead time, is 10 seconds. The current HSRP priority is 100. And this is group 1. Authentication is default with the password of Cisco. We haven't applied authentication in this particular case, but if we did, that would be the password, and then the virtual IP address is 1.1. All right. Now, if you look at layer 2, this is very important as well. We notice that the destination MAC address is 01005E, which is a OUI for multicast, and it is 000002. Remember, the last 23 bits of the IP address become the last 24 bits of the MAC address. All right? But the source here, this is really important as well. This is the well-known MAC address for HSRP, 00000 Charlie, 07AC01. And actually the last 8 bits, these last 2 nibbles, the 0 and the 1, that directly corresponds to the group number, right? So we have 8 bits that are available for the group number in HSRP version 1, which means we have 8 bits within the MAC address that are going to be reserved as the source for that particular group. All right? So let's go ahead and apply the rest of our filters here. Let's get rid of apply filter and not selected. And let's get rid of EIGRP, apply filter and not selected. And one more, get rid of our loop, apply filter and not selected. So now we're just seeing our HSRP messages here. Okay? So I'm going to go into router 2, and I'm going to apply the configuration to router 2 as well. Config T, interface Ethernet 1.1. The IP address on this interface is going to be 192.168. 1.2.255.255.255.0. And we're going to do a standby 1 IP 192.168.1.1. Okay, so we should now start to see actually messages going back and forth. We should see messages from 1.3. We should start to see messages from 1.2 as well. Let's apply filter and not selected. All right, so you can see here that 1.2 is in the speak state, then 1.2 goes in the standby state, and then 1.2 goes in the advertise, hello, and now we've basically ended up in the standby state at this particular point. Now, if I look at the information coming from router 2, I can see that it essentially has exactly the same information. It's a hello, 3 and 10, priority 100, group 1, virtual IP 1.1. So I guess the question in this case is, how did router 1 maintain its role as the active router, and how did router 2 lose its, kind of lose that role and became the standby router? Normally what we would do to influence the election process, outside of configuring preemption, which we'll talk about a little bit later on, but normally what we would do to influence the process of election is we would change the priority. The priority indicates who is going to be likely the active router. And it's whichever router has the highest priority would likely become the active router. Okay? Now, in the case of HSRP, it's not quite like that, because with the case of HSRP, the election process is non-preemptive, meaning that if you become the primary router, you will stay the primary router even if somebody comes along later with better values within the group. All right? So because router 1 was configured first, it became the active router. It stayed that role. Now, router 1 does have a tiebreaker, right? If you look at the IP address on router 1, do show IP interface brief, it has an address of 1.3, and on router 2, do show IP interface brief, it has an address of 1.2. The tiebreaker in HSRP is whichever one has the highest address. All right, so in this particular case, router 1 would have won anyway. We can also verify who actually is the active router without using show standby if I simply do a show ARP. And you can see here that the virtual IP address and the virtual MAC address exist on this router with a dash as the age. When you see a dash, that indicates that that is a value that's local to that router. In other words, that's a value on that router itself. If I were to go to router 2 and do a show ARP, I would see that the 1.1 address, let me go ahead and ping it. I do need to communicate to it in order for it to show up in the ARP cache. But you'll see for the 1.1 address here that we don't have a dash, we have a 0. And that number will continue to increment. It's an incremental timer to describe the age of the entry. So the IP address and the MAC address will go to the active router. Okay? Again, that MAC address, the format is quad 0, 0 Charlie, or 0 Charlie 07, Alpha Charlie XX, where XX represents the group number, and so on. And because we are using HSRP version 1, we're limited to that group in this particular case. All right. So there's a couple of things we can do now to test this. All right. All the routers in the group have really specific roles in this environment, right? The virtual router is basically just an IP and a MAC address pair that end devices have configured as their gateway. And then the active router processes all the packets and the frames that are sent to that particular virtual router IP address, right? The virtual router process has no physical frames per se. So within that HSRP group, like we said, one router, in this case router 1, gets elected as the active router, and then that active router is going to respond to all of those messages. Now, during a failover transition, a newly active router will send 3 gratuitous ARP requests. This is really important because we want to make sure that the layer 2 device learns about the new port that the virtual MAC address is going to be associated to. So if we were to force a failover event, router 2 would take over the role. We would get those gratuitous ARPs going over to the switch, which would indicate to the switch where that MAC address is. Okay? Now, how can we make sure, without relying on the tiebreaker of IP address, how can we make sure that a router is going to be the primary router? The active router election is based primarily on priority. And this priority can be anywhere from 0 to 255. As we've already seen from the outputs here and the debugs, or the captures I should say, the default priority is 100. All right? So let's go ahead and we'll modify this configuration in a minute here, but on router 2 actually. But to set the priority, we're going to use the standby command. In fact, pretty much with just about every command related to HSRP, we are going to use the standby command. And you can see here there are many, many different subcommands available with standby. So we're in group 1, and we're going to set the priority in this particular case. Let's just go ahead and set it to 110. Okay? Now this is, I would say it's somewhat of an arbitrary value, meaning that there is no significant difference between 100, 110, 120, and so on. It's just a matter of whomever has the highest value. They're more likely to become the HSRP active router in an environment. I say likely because it's not guaranteed. Because if I do a show standby, I can see that I'm in group 1. My current state is standby. The standby router is local. The active router is 1.3. It has a priority of 100. I have a priority of 110, but I did not become the active router. Okay? There is another feature within HSRP called preemption. Preemption allows a router to take over the role as the active router if it has better configured values and the router is functional, right? So router 2 is completely functional in this case. It has the ability to operate, but it doesn't have preemption enabled. So even though it has a better value, it will not take over the role as the active router because preemption's not enabled. So let's go ahead and enable that. We're going to go standby 1 and we're going to say preempt. All right. Now you'll notice as soon as I do that, that router 2 takes over the role as the active router. Preemption is disabled by default. And you would typically want it enabled in fact, almost always you'd want it enabled on both platforms. Now, there is actually no way, as long as router 2 and router 1 are functioning, interface Ethernet 1.1, standby 1 preempt, oops. There is no way that router 1 would ever preempt router 2 in the event that router 2 and router 1 are both available. Because the only way you can preempt another device is if you have better operational values, better operating HSRP values. And if I do a show standby, the standby router has a priority of 100. I have a priority of 110. So router 1 would not preempt me. But I'm going to demonstrate in a little bit why we would want to configure preemption on both devices. It's a very important concept. All right. Now, let's see here. The timers are important as well. Now, the default timers are 3 and 10 seconds. So we're sending hellos every 3 seconds, and we are our dead timer is 10 seconds. That is pretty significant, actually. If you think about most modern network architectures, waiting 10 seconds to do anything is a little bit ridiculous, quite honestly. All right? So it's very important that we kind of tune these timers. Typically, we'd want to make sure that these timers should take into account other convergence events like spanning tree convergence events, your IGP routing protocol convergence events, and so on. All right, but there's two things that we're going to talk about here. We're going to talk about the preemption values or preemption delay timer, and we're also going to talk about modifying the hold and the hello timers. Now, the hello message itself contains the priority of the router. The hello time, the hold time parameters, we saw that when we did our Wireshark capture. The hello time parameter value is an indicator of the interval of time between each of the hello messages that we're going to send. The hold time parameter is how long the current hello messages are considered valid. So if I don't get a hello within 10 seconds, I'm going to consider that you no longer are available, and I'm going to take whatever necessary action to manage the group in that particular case. Now, in most cases, we would like to adjust these values. The default times of 3 and 10 seconds means that a failover event could take as much as 10 seconds before clients can start communicating with their new default gateway again. And this is definitely, well, I would say for most applications is going to be way too long. All right, so we can adjust these parameters. They do have to match between the devices, so it's important that you make them match. Otherwise, the devices will not join the group. All right, now for the fastest convergence time, these timers should really be configured to their lowest possible value. And that's one of the major differences between, not GLBP, we don't talk about that in this class, but VRRP and HSRP is how we can tune these particular timers. All right? Just keep in mind that decreasing the timers do allow first hop failure detection to happen very quickly, but it also means there's going to be more overhead and more traffic. Now we would basically go into our interface and we would use the command standby group 1 timers msec, because we want to specify sub-second timers, and then we would simply specify our hello and hold time, and typically the hold time is anywhere from 3 to 4 times whatever the hello time is. All right? You also have to take into account other parameters that are relevant to network convergence, right? The HSRP timers may have to run in conjunction with some sort of dynamic routing protocol, right? The routing protocol has really no awareness of what's happening with HSRP. It sees both routers as basically just individual hops towards different networks. So if HSRP a failure event occurs, before the dynamic protocol can converge, you may get suboptimal routing and so on. That would also apply, by the way, if you are dealing with things like spanning tree and making sure not only that the spanning tree topology mirrors your first hop redundancy topology, but also that the spanning tree timers are typically sub-second are going to be in, congruent with whatever you're doing in HSRP. So let's go ahead and go into Ethernet 1.1, and we're going to go in here and we're going to say standby 1, timers, MSEC, and I typically will do something like 250 with a 750 millisecond hold time. All right, and I'll do the same thing on router 2. Ethernet 1.1. And we'll see from our Wireshark capture that we're going to be getting a lot more information. Now, these are relatively benign datagrams, so I don't necessarily consider this to be a huge deficiency, especially when we're probably going to be running gigabit Ethernet anyway, but our convergence events are going to be much, much faster. Now, preemption. Preemption is basically, hey, I'm the primary router. I go down, you take over the role as the active router, I come back up, I can retake over the role as the active router, right? But it is entirely possible that HSRP might think that everything is functioning because we have some sort of keep alive reachability, but the router hasn't fully booted up, not all the interfaces are operational, our Icmp Protocol hasn't converged, or we're running BGP or something like that. Upstream links haven't come up. You know, there's lots of things that could force a router to, or indicate that a router is functioning when it may not actually be functioning. Preemption is something that occurs as soon as a keep alive is sent and received. All right? But we may want to make sure, number one, that the device is fully functional and operational. We also want to make sure that the device is not flapping. So it's going up and down, up and down, up and down, which means that essentially we're constantly reconverging. All right, so we can do something in HSRP which will delay the preemption value. All right, so we should generally set the preemption delay to some sort of number that's about 50% greater than the boot time of the device. And you would have to calculate that, right? You'd actually have to base, there's nothing documented that says a device is going to take this long to boot up. It depends on how much memory's in that device, what type of operating system you're running, all the different features you're running on that platform, how many interfaces you have, and so on. All right, but at least with a 50% margin, you have a pretty good idea that that device is going to be operational before it actually does the preemption. And we can do this configuration just by going standby 1, preempt, standby, there we go, preempt, delay. And we can specify the delay in seconds, all right? Let's do a minimum here, sorry. And we can specify that delay as in seconds, all right? So that means to say that if a standby or if a failover event occurs and the router goes down, the router comes back up. This, by the way, this preemption value does not have to match on the peers, but it should kind of, right? Makes sense. That it's going to take 300 seconds before we actually trigger that preemption. It's kind of an important thing. So if I go into router 1 now and I just simply do a show standby, I can start to see all of those different elements that I've configured, right? 4 state changes. This is the virtual IP. This is the virtual MAC. I'm not the active router, so it's not in use on this device. There are my adjusted timers. Preemption is now enabled with a delay of 300 seconds. My priority is 100. The active router is a priority of 110. So it's a really, really useful command. It allows us the ability to see all kinds of all the configurations, if you will. Now you can also do brief versions, show standby brief. We don't get as much information, but we do get some of the key elements of the configuration here. All right. There are actually 5 different states that an HSRP router can be in. It can be in the initial state. That's basically the state at the start. Or if it's the state after you've done some sort of configuration change when the interface is first coming up. Then you go into the listen state. The router knows the virtual IP address, but it's now listening for hello messages from other routers. You go into a speak state where the router sends periodic hello messages and then actively participates in the election of the active or standby router. Standby state means that I became the next best router, if you will. I still send periodic hello messages, but this is one of the primary states that I would be in. And then the active state is the one that, of course, is the active router. All right? When a router exits any one of these states, it performs the actions that are required by that particular state. And not all the HSRP routers in the group are going to transition through all the states. If I have a group with 3 or more routers, a router that's not the standby router or the active router will basically just stay in the listen state. Right? So it doesn't matter how many devices are participating in HSRP, only one device can be active, the other device is standby, and the other routers are going to be listen. All right? All routers actually start in the initial state. This is the starting state, and it basically indicates that HSRP is not running. All right? Whenever you make a configuration change, if HSRP is disabled on the interface or when HSRP is enabled, it's first brought up. When you do a no shutdown command, these are all things that would trigger that. Now, the purpose of the listen state is to figure out if there are any active or standby routers that are already present in the group. In the speak state, the router's actively participating in the election, meaning it's actively telling everybody about itself. Each router uses 3 times, 3 values, I should say, or 3 timers, I guess, for HSRP messages. All right. Hello messages when a timer expires and when I transition to a new state. All right. So let's say router 1 starts up in this case. As it's the first router in the broadcast domain that's configured in group 1, it transits through the listen and speak states and then becomes the active router. Router B, or router 2 in this case, starts up after router 1. When router 2 is in the listen state, router 1 is already assuming that the standby and then the active role, because there is an active router already present. We saw this when we did our initial configuration, by the way. Router 2 assumed the standby role. Now, when the routers are participating in an election process, a priority like we did, could be configured to determine how the routers become active. Without that specific priority configuration, each router is going to have a default priority of 100, and then the router with the highest IP address would be elected as the active router, the highest IP address within the broadcast domain. All right? And we also talked about the whole concept of preemption and whatnot. Okay? So we could trigger some events here. We do have a preemption delay of 300 seconds. We'll probably have to take that out. In fact, I am going to take that out only for demonstration purposes because I don't want to have to wait for a specific period of time for the preemption to take place. All right. Now, there's a couple of things that we can do to trigger an event here, right? We know that router 2 is the active router in this case. So if I simply go into the interface and I shut it down, router 1 is immediately going to go into the active state. Remember, our dead timer is 750 milliseconds at this point. All right. We also have preemption enabled, and we took out the preemption delay, so it should take over the active role relatively quickly. In fact, it became active before the 2-second timer that iOS uses to identify the state of an interface and before our EIGRP neighbor adjacency came up. So this is a pretty quick failover event. All right. Now, there are a few other things that I want to mention. That's basically everything that they did in the ENCOR discovery, but there's a few other things that I want to talk about that I think are really important. First of all, we would generally want to run HSRP version 2. So if I do standby and question mark, you'll see that one of the options I have is to run version 2. And I would do this on both routers. Standby version 2. They are not compatible with each other. All right. Notice that we actually saw that both routers were claiming the virtual IP. And notice here now in our capture, there's a significant difference here. First of all, we see HSRP versus HSRP version 2. Also notice a couple of things here actually. The port number is the same, 1985. The time to live, let's expand our packet header. Time to live is 1, still UDP. But notice the destination IP address, 224.0.0.102. That is a group-specific multicast address for HSRP. Also notice that the MAC address changed, 00010C9F F001. So this is the group-specific MAC address, or the, I guess, assigned MAC address for HSRP version 2. Another important thing is we now have, in fact, let me show you here, standby question mark, I have a 12-bit value for the group number field, which means now I can really match my VLAN IDs to my HSRP groups. And in the Wireshark Capture, we don't specifically see this, but the last 3 nibbles, which would be 12 bits because each nibble is 4 bits, the last 3 nibbles are used or reserved for the group address. In our case, it's group 1. So that's one of the major differences between, say, HSRP version 1 and HSRP version 2. The other difference would be, say, for example, well, the timers are the same, right? In fact, if I do a show standby, we use the same command to verify everything. The timers are the same, so it uses our configured timers, but if they weren't configured, they would be the same, 3 and 10 seconds. And the priority values and the meaning of priority is the same. The only major difference is a slight difference with authentication, also the difference in the group size. Okay? Now this is another kind of interesting concept. If I were to go to PC1 and I would ping 192.168.1.1 as an example, which is the virtual IP, and I do a show ARP. Now this is a router, but let's assume it's a PC, right? If I was an attacker, I would look at this and I'd say, oh, okay, I know what that MAC address is. That MAC address is HSRP. I happen to know that that MAC address is HSRP version 2, which also means I know what the multicast MAC or IP address is, and I can start to craft some packets or datagrams to try and influence the election and maybe insert myself into a conversation or whatever else it might be. So my recommendation in this case would be to go into the standby group and specify the MAC address manually. Now I'm going to use an easy one so it's easy for me to remember on both sides, because but you would probably want to use something that looks a little bit more random. And now if I do a ping to 192.168.1.1 and I do a show ARP, I don't see that MAC address anymore, that well-known MAC address that all the attackers are going to know that they can use to make some sort of attack on the network, right? So just something to keep in mind as part of the process, as far as hardening the configuration and so on. Something to keep in mind. Now there is one other major piece, and I could certainly spend a lot of time talking about this, probably another hour, but I'm going to do kind of a brief discussion of this for now, and then hopefully we'll see this in our advanced routing and switching class in more detail later on. HSRP is running here. It's running on the broadcast domain, right? So if, for example, R1 and R2, as long as they can see each other within that LAN, HSRP is going to function correctly. But what would happen if this upstream link were to fail? See, router 2 is our primary router. So let's say this one. This link were to fail, right? Does that affect the HSRP group? Does it affect the keep alives? Absolutely not. It does not affect the group or the keep alives. So in the event that this uplink fails, Router 2 would still be the active router for the group. Traffic would be sent to router 2, and then router 2 would either have to do some sort of redirect or reroute that traffic over to router 1, and now we have suboptimal routing. Now, what I need to do in order to make sure that this works is I need to put in a static route. Now, normally I would not put a static route to an Ethernet interface. Let's do this. Show IP interface brief. So that's going to be Ethernet 1.0. Let's just go to router 3, show IP interface brief. So it's .2 and .2 respectively. Okay. So what I'm going to do is I'm going to do IP route. And let me go ahead and grab that address again. I would probably do this a different way if this was a production environment. You know, I would set up some probes in IP SLA and a bunch of different things to make sure that this route is appropriate. But right now I'm just doing something quickly here. And I would do the same thing on the other router. I'll explain why I'm doing this in a second here. And this is going to go to 3.2. Router 2. 3.2. Show IP EIGRP neighbors. So we are running EIGRP on the LAN side, which means that if a failover event occurs, EIGRP would basically reroute the traffic for that host, and we would not see the effect of an upstream link failure without any kind of interface tracking. So what I'm going to simulate here now is we've got HSRP running correctly within the group, and R2 is the active router for the group. We can come back to here and do a show standby real quick. And we can see that R2 is the active router for the group. And what I'm going to do is I'm going to shut down this link that goes to R2. Show CDP neighbor, this link that goes to R2, which is Ethernet 1.1. So config T interface Ethernet 1.1. I'm going to shut that down. Now, you'll notice that upstream link failed, but it did not affect the group. The state of this router is still active. So if I go to PC1 and I do my ping, oops, let's ping, let me see, do I have it still cached here? Let me try it. Nope. Let me go to the server, grab the IP, and go to router 1, and let's do, not router 1, PC1. And we're going to ping that server host, all right? Now, the ping should actually fail here, because what's happening is the traffic is going to router 2. Router 2 has a static route that points to that next hop, and because that static route is there, the packet cannot go through. So what I would like to do is I would like to set up a way to force an election to take place here based on an event that occurs here. Does that make sense? This interface is down, so there should be a way to force R2 to lose its role as the active router. And there is, all right? So we're going to go into router 2. Now, this isn't really the purpose of this discussion, so I'm not going to go through this in a whole lot of detail. I'm going to kind of just leave all the defaults and everything, but what I'm going to do is I'm going to set up an Ip Sla Probe, all right? And we're just going to call it number 1, and we're just going to make it an Icmp Echo Probe, and I'm going to ping this address, and yeah, we don't really need to set any of the thresholds. And let me see if I want to change any of the other values here. Timeout values, threshold, no. I mean, we could go and kind of adjust some of these, but I'm not going to do that right now. We're just going to leave it in the advanced routing class. We'll talk more about IP SLA and so on. So we're going to say IP SLA 1, and we want to make sure that we schedule this probe. IPSLA schedule, we want to specify number 1, the start time is going to be now, and the lifetime is going to be forever. Do show IPSLA 1, excuse me, oops. Let me do this. Show IPSLA summary, that's what I wanted. All right, so we can see we have an Icmp echo, and it's timing out. Tie this into our HSRP configuration. The next thing I have to do, by the way, if I do a show run section SLA, I basically just did a couple of things, right? I just set up an IPSLA probe, which is basically just to do a ping. If I was doing this in the real world, I'd probably set up a group of addresses to ping. I might even set up an IPSLA responder so I could measure things like delay and jitter and packet loss and stuff like that. But we're just doing a basic demonstration here. The next thing I have to do is I have to set up a tracking object. And I'm going to use track 1. And we're going to base it on IPSLA 1. All right? And we want to make sure that we are tracking the state, right? The state of the IPSLA probe. So if I do a show track, I should see, I should see that the IPSLA probe is down, which means that the tracking object is down. All right? Now again, I could modify some of these parameters if I wanted to. That's not really the goal here. Again, we're just doing a very quick and basic upstream object tracking example so that we can show you how it gets applied to the HSRP configuration. So we've set up the probe, we set up the tracking object. Now we're going to go into Ethernet 1.1. We're going to say standby 1, track 1, which is the group, and then we're going to decrement the priority value. Now if I hit return here, the default decrement would be 10, which means that technically router 1 should take over, because if I decrement my priority by 10, router 1 would have the higher IP address. There would be a tie in priority. Router 1 would have the higher IP address, so it should take over as the active role. But I'm going to decrement by 20 just to make sure that because the tracking object is down, based on the Icmp echo probe that we created, I'm going to change the default priority of this device from 110 to 90. All right, now you will notice right away that router 1 became active. I told you guys before, set preempt on both devices, right? Set preempt on both devices. Why is that important? Well, if I didn't have preempt on router 1, it would not take over the role as the active router because HSRP is still working. Router 1 and router 2 are reachable. But because I have preemption on router 1, and now router 1 has a higher priority, show standby, because of the decremented value on router 2, router 1 became the active router. So I should be able to ping now to my destination. Okay? Now, if I go back to router 3 and I do a no-shut on that interface, the tracking object should come up. This is where tuning the timers and all that should be important, right? Because normally I'd want router 2 to become active more quickly. Oh, we would probably have preemption delay on anyway, so it doesn't matter. But because the probe went from down to up, the priority is no longer decremented on router 2, and because it has preempt, it took over the active role for the group. Okay? Now, there are many, many other things that you can configure. You can set up the name of the group. If you want to have a group redundancy, you can set up v6 properties. You can set up authentication. We don't have time to go through all that in this particular discovery. Certainly, if you take a look at our advanced routing course, you're going to see some more details about that in there. But that pretty much concludes everything that we're doing with HSRP here. We're going to go ahead and get into a brief discussion of VRRP, and then we're going to do a VRRP discovery, and we're going to wrap up this lesson. So we'll see you guys in the next section. So there are some advanced features that we can run. I kind of alluded to these as we were talking about HSRP. What are the advanced features? Upstream tracking is one of the most advanced features that you can implement. Remember, just because an event doesn't occur downstream doesn't mean that the network is in a good state, right? So we're, in this case, router 1 and router 2 have HSRP configured on this downstream network. If this link fails, we don't want router 2 to be the active router in this particular case. I would rather have router 1 take over the role as the active router until that link comes back up. Well, that's not going to happen based on an HSRP event. That has to happen based on some sort of object tracking and so on, because we'll end up getting this kind of suboptimal routing. I'll send the traffic up here. This guy will send a redirect over to here. It's not the best option. All right. So how can we manage this process, based on these changes that take place? Well, we can either do object tracking or we can just do native interface tracking. I prefer to use object tracking because it allows me to track the whole path rather than just the status of the interface that the router is connected to. So I prefer to do verify the whole path. And that could be like an Icmp echo probe, IPSLA Icmp echo probe, where we're just pinging, maybe an address along that path or an address at the service provider level, where we have maybe a static route that says, go ahead and send this particular ping out this interface. And if the ping fails, the tracking object fails, and then we can decrement the HSRP priority based on that. So in essence, what we'd like to do is we'd like to have a priority of 110 here and a priority of 100. We'll set up IPSLA on router 2 to ping the server or ping some upstream object with IPSLA, set up a tracking object, and then go into this group configuration and say, if that ping fails, by the way, you would need a static route here because if this interface fails, most likely the ping would end up going over this way anyway. So you need some sort of static route here to enforce the ping to go that way. But if that ping fails, let's go ahead and decrement the priority down by 20, and then the other router will simply take over because it has preemption enabled. That's why you would want preemption on the backup router. So if I decrement this priority by 20, this router on the left will take over the role as the active router, and everything is copacetic, right? So how do we set that up? Well, we just have to set up IPSLA, we have to set up a tracking object, and then, of course, make sure routing is configured appropriately to handle that as well. If I don't specify a decrement value, if I reference an object and I say, go ahead and decrement, but I don't specify a decrement value, the default decrement value is 10. That might work in this case if this router had a higher IP address than this router, because the tiebreaker would be IP address, but usually you try to decrement by enough to ensure that the other router is going to take over as the active router. All right. So HSRP provides a solution to this particular problem by using interface tracking. Again, I prefer to use object tracking instead of interface tracking. Interface tracking literally can only trigger an event if the link state of the upstream interface, the directly connected upstream interface, actually goes down. Well, that's just one possible problem, right? There could be many problems. There could be a routing issue. There could be a latency issue. The service provider might have a routing problem. So by just doing interface tracking, you're not going to be able to see that, all right? We already walked through the scenario. So this would be the configuration in this case if we were doing specific interface tracking. Preempt on router 2. All right, now preempt is on router 2 so that if the interface comes back up, the priority is going to increment back to 110. I want that router to take over as the active router. All right, but we'd still need preempt on the backup router as well. So our normal priority is 110. we're tracking the line state of Ethernet 00. If the line state goes down, decrement the priority by 20. If I had not put 20 here and just hit carriage return, then the decrement value would have been 10. Again, that might have worked depending on what the IP addresses are on the interfaces. All right? Totally depends what the IP addresses are on the interfaces. All right? Pretty simple configuration. If we were tracking an object, I would just put the tracking object number instead of the interface. I would just simply put the tracking object number, and that's how I would be able to identify the decrement value. All right. I don't know. Maybe when we get to the advanced routing piece, we'll talk more about that. But I don't know. I don't know if they get into that or not. All right. There's plenty of examples online, though. If you want to Google HSRP object tracking, plenty of examples online to see that. Okay. Let's see. To disable tracking, no standby group track. Load sharing. Now you can do load sharing with HSRP, but it's a static, it's a manual load sharing. There isn't, and it's called MHSRP, which is multiple hot standby routing protocol. But basically all you're doing is setting up multiple groups, and you're making one group the active group for one VLAN on one router, and the other router is going to be the active router for the other VLAN, and then they fail each other over. That's the best way that you can do load balancing with HSRP, as well as VRRP, by the way, because you can only have one active router in the group. So it's not going to be perfect, but it's better than just polarizing all the traffic over a single link. All right. So what they're showing us here is they're saying, okay, let's go ahead and set up this MHSRP. Let's make sure that switch 1 is the root for VLAN 10, and switch 1 is also the active router for the subnet. Let's make sure that switch 1 is the secondary root for VLAN 20, and let's make sure that it is the backup router or the standby router for the HSRP group. So you notice how they kind of married the spanning tree topology design with the routing design. Now they didn't marry the timers. I would have done that as well, just to have a complete, concise configuration. I would have made sure that I'm running rapid spanning tree, and I would have made sure that I adjusted my HSRP timers to match my expected convergence time for spanning tree. And then it's kind of like a mirror configuration on the other side, where we specify root primary, root secondary on the other side. All right. You can do it within the group as well. You can actually have multiple groups within a subnet. That's a little bit more challenging because you would have to have a different group number, and you would have a different virtual IP. But it would be within the same subnet as the other group. And in that particular case, the way that you would ensure load balancing is you would have to have the clients themselves would actually have to have either different DHCP scopes within the same subnet, or you'd have to statically configure the gateways on the clients to point to those different virtual IPs. Now we can do authentication as well. Plain text, of course, is not recommended. That would mean that the password is passed in the messages. MD5 authentication is preferred because we never send the keying material over the link. All we're sending is a hash with the messages. Now, authentication is not encryption, and it doesn't necessarily provide integrity, although it kind of provides integrity because the hash that's being generated is based on the message that's being generated and special keying material, right? The keying material would be the actual key string that you configure. So the way that it works is basically I generate my HSRP message, and I take that message. Before I send it, I take that message and I take the key string and I put them into a hashing process, and then I generate a MAC, a message authentication code, or a hash output, and I just simply send the hash with the message. On the other side, I receive the message. I also have the key string configured. I run it through the hashing process. If the hashes match, if the hash that I generated matches the hash that was sent, then the message has been authenticated. And in essence, the integrity has been authenticated as well, because if evil Eve in the middle somehow tried to modify that message, unless they have the key string, they're not going to be able to generate a valid hash that could be verified by the recipient. So it's very important that that key string be kept secret, and it's never shared, and that it's relatively secure. I mean, hashing processes are difficult to break anyway. Typically we use a rainbow table or some sort of brute force type of attack to do that, but if you're using basic passwords like Cisco, that would be a very easy thing to do. All right. So we set up the key string, standby 1 authentication, MD5 key string, very secret password, and then we simply apply the authentication to the group. Now, if we were doing plain text, we wouldn't have to set up a key string. We would just say standby group authentication string, but that key is going to be sent in the messages. So, and if you're doing a Wireshark capture, or if you're just capturing data, you're going to see that information very easily. Okay? Apply that to the group, and then you're good to go. All right? Now, we can use a keychain as well. The keychain allows me to rotate through keys if I want to. The concept of a keychain works with just about any MD5 authentication process. EIGRP and OSPF can reference a keychain. HSRP can reference a keychain. And I believe, if I'm not mistaken, could be wrong, but NTP can also reference a keychain. The nice thing about a keychain is that you can configure multiple key strings, and you can specify key lifetimes. So you can say, okay, this key is valid from this date to this date, this key is valid from this date to this date, and then you end up rotating keys. The only downside to that, of course, you have to make sure that everybody's timers are synchronized, otherwise you're going to have a big problem. All right. HSRP versions, oh, they finally gave us the information. All right. There's the same information that we talked about previously. X is the group number, 12-bit group number, supports dual stack. HSRP version 1 only supports v4. Generic multicast group, group-specific multicast group. All right. If I want to switch to version 2, I simply run the command standby group number version 2. They're not compatible with each other, right? They have a completely different packet format. They use a completely different group address, so they're not compatible with each other. All right. What are the two supported types of HSRP authentication? Plain text, or in the clear, and MD5. All right, guys, welcome back. We are now moving into discovery number 13. And discovery number 13, we're going to be talking about the virtual router redundancy protocol. All right, it is basically an open standard alternative to HSRP. So very similar to what we've talked about with HSRP, not a whole lot of differences. The configuration is also very similar. So I would encourage you to take a look at the HSRP discovery video or section of this video prior to going through this particular section, because a lot of the things that we talk about are very similar in this particular case. We're probably not going to do as deep of a dive in this particular case for this protocol. All right. VRP is really, really similar to HSRP, not only with its operation, but with its configuration as well. The VRRP master router is basically the same as the HSRP active router. The VRRP backup router is the same as the standby gateway that we have in HSRP. A VRRP group in this case, though, has one master device and one, or in the case of VRRP, slight difference here, multiple backup devices. The device with the highest priority becomes the elected master. Preemption is enabled by default. Unlike HSRP, the priority number can be anywhere from 0 to 255, just like HSRP. The default priority is 100. Now, in the case of VRRP, the priority value of 0 has a special meaning. All right? It's actually a way for us to indicate that the current master has stopped participating in the VRRP group. And this is what we use to basically trigger backup devices to quickly transition to the master role without having to wait for the current master to time out. So that's something that we didn't see as an availability, as an option in HSRP. VRRP also differs from HSRP in that it allows you to use the address of one of the physical VRRP group members as the virtual IP address. The device with the used physical address is a master whenever it is available, but when it loses its connectivity, when it becomes unavailable, somebody else can take over that IP address. The master is actually the only device that sends out advertisements in this case. An advertisement in VRRP is analogous to like an HSRP hello packet, right? Advertisements get sent out to a group-specific multicast address in this case, 224.0.0.18. We use protocol number 112. So this is actually not encapsulated inside of a transport layer protocol like UDP or TCP. It's actually encapsulated directly inside of IP. Anytime you have a protocol number, that's going to indicate, other than 7 or 17, or 6 or 17, I should say, which is TCP and UDP respectively, it's going to indicate that it's encapsulated as its own layer 3 process. All right, the default hello interval is 1 second, and the hold time is 3 seconds. So we still have a three times multiple on the dead timer, but certainly the hello time is much lower, well, at least 3 times less than what we would see by default in HSRP. All right, HSRP, if you recall, uses timers of 3 and 10 seconds. Now, although VRRP is a protocol that's defined on based on RFC 3768, the RFC itself says that the protocol does not support millisecond timers. We talked about the benefit of adjusting to millisecond timers when we went through HSRP configuration. Cisco does provide us the ability to configure millisecond timers in VRRP. We have to manually configure the millisecond timer values. They do have to match, so we're going to have to do that on the master router. We're going to have to do that on the backup devices as well. And we're going to use those millisecond timers, kind of to speed up the convergence process. The millisecond values work only under favorable circumstances. So you have to be aware of when you're to use those millisecond timer values. And of course, if you are using millisecond values, it is going to limit you to running VRRP only on Cisco devices, because other devices are not going to support that functionality. And the timers do have to match in order for the routers to be participating in the same. All right. Now, when you do use the millisecond values, the master advertisement value that gets displayed in the show VRRP command output, if we look at that on the master router, we're going to see the value that we set. If we look at it on the backup routers, it's always going to be 1 second, even though the actual configured value might be different. So that's just something to keep in mind as you're troubleshooting and verifying the operation. So in our particular example, we have layer 3 devices, right? A, B, and C, or in our case, 1, 2, and 3. They're going to be configured as VRRP virtual routers. Actually, we only have 2 in this case, R1 and R2. But let's say, for example, we did have a third router, right? R1, R2, and R3. And they're configured as VRRP virtual routers, and they become members of the same group. Because R1 would be configured, or let's just say we did configure R1 with the highest priority, it's automatically going to be selected as the master router for the VRRP group. The end devices are going to use that particular device as their default gateway. For router 2 and router 3, for them to function as virtual backup routers, or virtual router backups, I should say, we would have to, of course, configure them to be part of the same group and then set up the appropriate properties for the environment to function the way we would expect it to function. So if the master fails in this particular case, any device that's left over within the group that has the highest configured priority would become the master and provide that uninterrupted service to the local hosts on the LAN. Unlike HSRP, though, by default, VRRP has preemption enabled, so when router 1 recovers, and that preemption, of course, has not been modified in any way, router 1 is going to become the master router again. We also have the ability, and this is one thing I really didn't talk about too much with HSRP, even though this is also an option available with HSRP, we have the ability to do load sharing, right? With HSRP, we can have multiple, with VRRP I should say, we can have multiple routers within the group. So we could configure, say, different clients, maybe it's client 3 and 4 to use a different gateway than clients 1 and 2 do. We could do that with HSRP as well. It's not very practical in a sense, because it is really a manual load balancing process. You would have to ensure somehow that those clients would get a different physical IP address as their gateway. That could be done through DHCP, but it might have to be done through some other method and so on. But the point is that you could have multiple layer 3 devices and different VRRP groups designated on those devices, maybe as one group for one set of hosts and another group for another set of hosts and so on. We're not actually going to get into that configuration in this particular case. In this discovery, we're going to learn basically just how to configure VRRP. We're going to take a look at the key differences between VRRP and HSRP. And then beyond that, most everything else is going to be the same. All right, so router 1 and router 2 are going to be our routers that we're going to set this up on. And we're going to start with that configuration. So let's start by configuring VRRP on the routers. I'm going to go into router 1 to start with. And I'm just going to do a quick show IP interface brief. Our downstream link is not configured. So we're going to go into config mode, interface Ethernet 1.1. We're going to give it an IP address of 192.168.1.3, a mask of 255.255.255.0. Instead of saying standby, we're going to say VRRP. Notice here, group number, 8-bit group number. All right, VRRP1, and the standby IP in this case is going to be a virtual IP. You'll notice as soon as I do that, the router is now running VRRP. Let me go ahead and start a capture on the interface as well, because I want to look at some of the other characteristics of the packet, so we'll let that run in the background. All right, so now we have VRRP running on this interface. Just like HSRP, VRRP uses the concept of a virtual IP to provide those end user devices with their first hop redundancy connectivity. The virtual IP address is configured using the command that I just executed. We can use one of the real IP addresses from the physical routers as the virtual IP address. So we could use 1.3, but that would mean that 1.3 would always become the active router, or the primary master router, I should say in this case, for the group as long as it was active. In the case of using a virtual IP, it gives us a little bit more flexibility. So we're going to do the same thing on router 2 here. Let me do a quick show IP interface brief. And we're going to go into interface Ethernet 1.1. And we're going to say IP address 192.168. Let's do 1.2 in this case. That'll make it the same as what we did with HSRP. And we're going to say VRRP1 standby, IP, excuse me, I'm mixing up my terms here, 1.1. All right. Now, in this particular case, we still go into the role of backup because the priorities are the same. If I do a show VRRP, you can see that the default priority value is 100 right here. Preemption is enabled by default. Notice the virtual MAC address that we're using as well. This is a well-known MAC address, and just like we talked about with HSRP, I have the ability, I should have the ability of either enabling or disabling preempt. I can set the priority, I can set the timers. I thought there was a way to actually change the MAC address as well, but it doesn't appear as though this particular version supports that. Let me see, VRRP 1 IP 192.168.1.1. Let me see if it's an extension of this command. VRRP 1 IP 192.168.1.1. What did I mistype here? Let's see, VRRP 1 IP 192.168.1.1. Why is it not taking that command? I am in interface Ethernet 1.1. Why isn't it taking my command? All right. Secondary address, but we don't have a chance to change the MAC address. I'm trying to figure out why that other command is not correct. It's really strange. It looks to be the correct syntax. I'm not sure why it's giving me an error in that particular case. Anyway, so MAC address is something that we can't change in this particular case. But again, router 2 became the backup router, not the master router in this case, because router 2 has a lower IP address. We both have the same priority. Now with HSRP, we could actually leave out the group number when we're setting up the configuration, and it will just simply default to group 0. With VRRP, there is no such default. You have to specify a group number, and it is any value from 1 to 255. Okay? Now I can also change the priority. We do that pretty much the same way by setting a priority value. We can see the priority can be anywhere from 1 to 254. I'll set the priority to 110 in this case. And we should see that this router will preempt the configuration and it will become the master router. All right, we can see that router 1 lost its role as master and it went to backup, and router 2 lost its role as backup and became master. And that is again because we have preemption enabled by default. The higher the priority on the device is going to indicate who should become the master for the group. All right, so R1 is left to its default of 100, so that means that router 2 takes over. Now, if I use one of the router IP addresses as the virtual IP, the priorities actually get ignored for electing the master. Whichever physical IP address I use that matches that device will always become the master for the group unless it's not available. All right? And again, preemption, like I said, is enabled by default. Just like we did with HSRP, our primary method for verifying this first hop redundancy is to do a show VRRP. All right, we can see pretty much it's kind of self-explanatory, right? This is the virtual IP, virtual MAC address, preemption is enabled, the priority is 100. If we look at our Wireshark Capture, and let's go ahead and filter out some of these, let's just say apply filter selected. So these are my VRRP announcements, and you can see that the layer 2 MAC address is the destination is based on the group number, the multicast group number, I should say, multicast group IP, which is 224.0.0.18. 18 would be a 1 and a 2 here because it's 16 plus 2, and 16 would be the 5th bit in an octet, which would mean that that nibble would be a 1 and 2 would be a 2. Right? The source address 000005E010101, the last 2 nibbles, the last 8 bits represent the group number. Notice the destination IP. Now the time to live here in this case is 255, unlike HSRP, which is 1. That doesn't necessarily mean this is routable. I mean, it certainly could be routable, but that's just simply not the function of the protocol. We can also see that there is no UDP component in this case. VRRP is encapsulated directly inside of IP. All right, so there's no transport layer component. It is an application that runs directly on top of layer 3. This is the virtual router ID. This is the priority. We're not running any authentication in this particular case. We got some checksums and so on. So pretty basic packet or payload type here, or payload information. You can see that the advertisements are every 1 second, 43, 44, 45, 46, 47, and so on, which kind of corresponds to what we've been talking about. Okay? Now, if I look at router 1, I can see the MAC address of the virtual router, just like we saw before. Let me do a quick ping to 1.1, and we'll do a show ARP. We can see that the virtual MAC and the IP, because we have an age here, same meaning here as we saw with HSRP. This is not the master router. I can also do a show VRRP brief, just like I saw with HSRP. Again, pretty much gives us the same information. This is the interface it's running on. This is the group number. This is the priority of the interface. This is the current state. Is preemption enabled? This is the master's IP. This is the virtual IP group address. Okay? Now, because pretty much everything else is the same with regard to the configuration, so if I go into interface Ethernet 1.1 and I say VRRP1 question mark, I can do things like preempt, no preempt, priority. I can do tracking, where I can track an object and do decrements, just like we demonstrated with HSRP. So because pretty much all that stuff we've already covered, I would like to cover one other aspect of VRRP that we did not see with HSRP, and that's how do we set up authentication. VRRP is used, it has multiple authentication options. You can either do plain text authentication, or you can do an MD5 hashing-based authentication. All right, now MD5 was actually removed from the RFC later on, but Cisco, again, still supports this option when you're configuring VRRP. So when the original RFC came out, 2338, plain text and MD5 authentication were available. 3768 and 5798 remove authentication support altogether, actually, from VRRP, but the Cisco implementation still supports the original RFC 2338 specification. So I'm going to say authentication in this case, and I'm just going to say text, and we'll just put in a password. Now, I'm going to do that. Obviously, we're going to have to do that on both of the devices, interface Ethernet 1.1, so that the group can function. But here's the thing about this authentication method. If I look at the actual announcements and I go and look at the VRRP information, I can see that information in plain text in the packet capture. So anybody running simple text authentication, RFC 2338 in this case, simple text authentication would be able to capture this information. So I'd prefer not to use this method of authentication because it's obviously not very secure. What I'd rather do is to do a authentication method with, let me get rid of that A there, with MD5 hashing. So I'm going to simply come in here and say VRRP1, authentication, MD5. Oh, this one doesn't support that version. Shoot. Well, what I would do normally, this particular iOS doesn't support it. What I would normally do is say MD5 key string, and then I would put in a key string. And what would happen in this case if this was supported on this platform? What would happen in this case is that the router would start to do send a message digest along with the messages that are generated. It doesn't do encryption. We're not hiding the messages, but we are sending a message digest. And then the receiving router is going to calculate, based on its own configured string, the same message digest based on the data that it receives, the VRRP data, and then based on that, it'll be able to verify or disqualify, say for example, messages that don't have the same hash. It's very, very similar to like a cyclic redundancy check or any basic hash-based authentication that you might see with things like NTP or EIGRP or OSPF. All right. So just a couple more things that we're going to talk about here. According to RFC 5798, operational experience further analysis basically determined that authentication did not provide sufficient security, if you will, to overcome the vulnerabilities of misconfigured passwords. So in that case, you might have multiple masters being elected and so on. And because of the nature of VRRP, even if VRRP messages are cryptographically protected, it doesn't prevent an attacker from behaving as if they are the VRRP master, which would then in turn create multiple masters in the group. So the authentication of the VRRP messages really could have prevented this, right? Because you would have to know the string, the secret key string, if you will, in order to be able to participate. All right. Independent of authentication, we also talked about the mechanism or the time to live of the packets themselves. The time to live of 255 is the default set. Now, VRRP actually implements another mechanism where we do time to live checking on the recipient to make sure the time to live hasn't been decremented, which is going to allow us to verify whether or not VRRP messages are being injected from another routing broadcast domain. We don't get into the configuration of that. Let me see if we can see that here. We don't see it here. Authentication. Yeah, unfortunately, we don't see the option here, but it is something that we could configure as well to do that time to live checking. All right, now with Cisco devices, the default authentication is plain text. MD5 authentication, if I had an advanced security image or maybe some other image with the different features, I would probably be able to do the MD5 configuration as well. All right, now with MD5 authentication, we can directly reference a key string from the authentication properties, or just like with HSRP, we can actually reference a key chain, which means that we can have multiple keys with different lifetimes, send and accept lifetimes, and so on. So we can get really complicated and complex configurations with key rotations and so on. So the command, like I said, is just VRRP1 authentication MD5 key string, and then you specify the key string. If I did this on one side and I didn't do it on the other side, I would see something like a bad authentication message, because one router has no authentication, the other one has MD5 authentication. So certainly you're going to want to do this on both sides of the link. All right. And to verify the authentication configuration, you would just simply do show VRRP. So just to reference again, I'm not going to go through the whole details of doing the static routes and all that, because I'm not going to actually demonstrate the functionality. But we could still do IPSLA1 echo Icmp echo probe, IPSLA1 Icmp echo. Let's just say it's 1.1.1.1 in this case, and then we say track 1 SLA1 IPSLA1, and then I go into interface Ethernet 1.1. I could come in here and say VRRP1 track 1, and then I do my decrement. All right, so it's the same concept, if you will. You create an IPSLA probe. Our probe is not going to work because we don't have that IP address in this topology, but you create the probe, you create a tracking object, and the same function is here, right? We decrement the priority based on upstream object tracking failures or probe failures, so that we lose our role as the master router. And then another router, a backup router within the group, can take over that, just so we can maintain optimal routing within the routing domain. Okay? So we didn't get into a whole lot of the other details with VRRP. We saw some of the message types and so on, but for the most part, if you're well proficient in how to configure HSRP, you should be just fine with VRRP as well. All right, so just a quick discovery. We'll go ahead and wrap this up, which means we're going to be wrapping up this lesson. So we'll see you guys in our next lesson, which I believe is network address translation. Well, that's the section that we're going to be going through. So we'll see you guys in the next lesson. All right, so we're going to take a brief look here at some additional features that we can add to our layer 2 devices to kind of decrease the amount of convergence time. Things like redundant route processors, stateful switchover, redundant supervisor modules, and so on. Some of these are related to hardware redundancy. Some of them are going to be related to kind of a mix of hardware redundancy and software redundancy. Having redundant supervisor modules, like if you have a 6500 series chassis, you can build redundant supervisors into that chassis, and they can kind of fail each other over. In addition, you can have like a switch stack, like a virtual switch stack between 6500s, or you can have a physical switch stack on a 3850 stack or a 9000 series stack, and so on. So what is RPR? That's the redundant supervisor function, where you have an active module and then a standby module, and it maintains stateful information about the flows that are going through that device. So with this redundant supervisor, the failover is almost immediate, right? Because it's powered up, it's already maintaining state information. That's where the stateful switchover concept comes into play. If I'm running RPR for my redundancy module, it says that the redundant supervisor is only partially booted and initialized. If the active module fails, the standby module must reload every other module on the switch. So in this case, there's going to be a huge impact to the failover during that failover event, but you'll at least be up and running again after a minimal amount of time. RPR Plus, kind of a middle of the road piece with RPR Plus. The redundant supervisor gets booted. It allows the supervisor and the route engine to initialize, but no layer 2 or layer 3 functions get started in this particular case. If the redundant or if the primary module fails, then the standby module kind of goes through its initialization and it reloads the other switch modules. And again, we're going to have a hit in this particular case. Stateful switchover is really where you want to be with Cisco nonstop forwarding, because both modules are active, both modules are functioning, and we're maintaining state information about flows, TCP flows, and session information on the redundant modules. So if the primary module fails, we have very limited downtime because it's going to fail over automatically to that secondary module with that Cisco nonstop forwarding. The routing information base, the caches, the adjacency tables, everything is going to get, the forwarding information base, all going to get rebuilt very quickly in that secondary module, and we can continue to process information. So they referenced here the 9400. This particular switch module does do nonstop forwarding with stateful switchover. So you can have redundant supervisor engines, you can have a primary and a secondary. All of the stateful information is continually synchronized, and that's the most important aspect that's going to provide you the ability to fail over with a sub-second time without having to reset TCP sessions and without having to lose communication. So the switchover actually is sub-second. It takes about probably less than 150 milliseconds. I know they document it at about 150 milliseconds, but that's kind of the high end. Anything less than 200 milliseconds will result in minimal traffic disruption. Most TCP sessions will recover from that, and so on. All right. So they got a pretty little diagram here. It says we're doing the constant synchronization between the supervisors. The uplinks stay up, less than 200 milliseconds of traffic interruption. The links for the devices stay up. They continue communicating. and we don't lose power over Ethernet. We don't lose really anything with this stateful switchover. That's why you pay the big bucks for this box, right? So stateful switchover minimizes the time that the network is unavailable, and you know, it is pretty significant if you have to physically reboot the device. About 10 or 15 minutes for that device to kind of boot up completely in it. If you have more than one module, it could be even worse. All right. So which of the following redundancy modes on a catalyst switch allows the standby module to finish initializing without reloading other modules? That would be the stateful switchover mode. All right. I don't even know why you would run the other modes. Perhaps if the platform doesn't support stateful switchover or nonstop forwarding, you might do it in that particular case. All right. So to wrap up this section here, we'll go through our summary challenge. Which of the following is a first hop redundancy protocol that Cisco designed to allow multiple active forwarders and load balancing outbound traffic? And that is the gateway load balancing protocol. Okay. In HSRP, what are the two possible states for the routers? Active and standby. Master and backup would be what VRP would use. What does a host without a dynamic routing protocol do when the only default gateway it has configured is unreachable? It stops working. I mean, it can't route off the local subnet, right? We don't use CDP. We don't forward packets to a backup router. If the gateway is not reachable, we simply can't route. Which of the following options is the default priority for VRRP? It's actually the default priority for all three. GLBP, VRRP, and HSRP have a default priority of 100. And with all three, the higher the number, the more preferred. Which command can be used to verify the status of HSRP? Show standby. All right. And then we get into our repeat question. So, oh, no, we've got a couple of new ones here, actually. Which of the following redundancy modes on a catalyst switch has the effect of the standby module reloading every other module and initializing all supervisor functions? That's the RPR function, right? Which of the following is the correct multicast address for VRRP? 18, 224.0.0.18. This is HSRP group 1. This is nothing. I mean, it is something, but it's not related to HSR or first hop redundancy, and that's also not related to first hop redundancy. Those multicast addresses belong to somebody, but not sure which ones. Which two of the following commands would set the authentication method for VRRP on an interface to use MD5? So VRRP 1 authentication MD5 key string and key string. Actually, this would be plain text, wouldn't it? So it would have to be I don't know the answer to this one. I've always just simply used this command. I have to look at the answer key for this one. I would imagine it would have the MD5 keyword, or MD5, yeah, it would have the MD5 keyword. This would be if you were doing plain text. So I would guess it's probably A. VRRP1 authentication MD5 key, because you can abbreviate commands, so that would basically be the same command, just an abbreviated version of it. That would be my guess. But which two commands could be issued on R1 to verify the HSRP group priority and the state? Show standby and show standby brief. And then now we're getting into our repeat questions. All right. So that wraps up that lesson, that topic. We'll go ahead and move on to the next topic. We'll see you then.